So, hello everyone. As the number of students are very less, so I will wait for 5 more minutes so that all of the people who want to join the call they may join. So I'll wait for 5 minutes. Then I will be starting the problem solving session. So in 5 minutes, we are going to start the session. I'm waiting for 5 minutes. Um, so that others can join. So I hope my screen is visible to you and I'm audible.
Yes,
So to let you know all that I will be starting the session 5 minute in 5 minutes as the many people are joining. So after some time, I'm going to start the presentation or the problem solving assessment. Sorry, the problem solving session. So just I'll be waiting for 2 to 3 minutes. Then I will be starting. So I hope all of you have gone through the lectures of week 2, which is being posted on your NPTEL platform. So you have gone through the lectures or not? Just please confirm. So I want your response at least yes, no, say something. So okay, I will be starting the presentation or today's class. So I am Himanshi Singh and I am from IIT Jodhpur. Currently, I am pursuing my PhD from Department of Mathematics, IIT Jodhpur, in broad area of probability and statistics. So I am your this teaching assistant for this NPTEL course, which is probability and statistics. And today I will be delivering a tutorial second, and I will be giving you a brief recap about the week two lectures, which has already been posted on this NPTEL platform. And after that, to understand the concepts better, I will be discussing some 10-12 problems with you, so that you just have a better understanding of the concepts. So we will be starting. So, in week two lecture, the concept of conditional probability based theorem, law of total probability, random variable, discrete random variable, probability mass function, probability distribution functions, all these things were discussed. So, first of all, this conditional probability was discussed. So, for that, this we consider. Let us consider that there's omega. BP is a probability space. So basically, this omega is the sample space, and this B is a sigma field, which is basically a class of subsets of omega, and it satisfy two properties which we have already discussed in previous lecture. So B is a sigma field, and P is basically a function from omega to R. So this is a probability space, and let F be in B, and with probability of is greater than 0, then we say, then for any event E in B, the conditional probability of E given F, given that F has already occurred, is defined as probability of E given F is equals to probability of E intersection F divided by probability of F. So basically, for a single event, we have already defined that what is the probability of this event. But if there are two events and we know that the second event has already occurred, and we want to find that what is the probability of event E given that F has already been occurred, then this notion or this concept has been defined, or it has been given by conditional probability, which is basically given by this formula: probability E given F is equals to probability of E intersection F divided by probability of F. So basically, the happening of F is having some impact on happening of E of happening of E. So let me just consider an example to have a good approach toward this. So let us suppose that a fair die is rolled. So what is the probability that two occurs? If I am considering that all the occurrence of the event, all the occurrence of the numbers are equally likely, then the probability that two occurs is 1/6. But if I consider that probability 2 occurs given that even number has occurred. So basically, even number has occurred. Probability. So probability that even number occurred. So basically, what is the event here? That probability. What is the event here? That 2 occurs, 4 occurs, or 6 occurs. So what is the probability of this event? That is 3/6, which is 1/2. So probability of this conditional probability will be what? That is equals to probability of the intersection. Let us consider that this to be an event E, and let us consider this to be an event F. Then this is E, probability of E given F. So probability E given F is equals to probability of E intersection F divided by probability of F. So what is probability E intersection F? That is what is E intersection F event? What is this E intersection F event? This is basically that even number and 2. So basically this is single. So this is basically a single 2, because what is E intersection F? That 2 occurs, and what is F? That even number occurred. So what is the intersection of those two? This is singleton 2. So basically the probability of E intersection F is probability that 2 occurs, that is 1/6. So here we will, so probability of E intersection F is 1 by 6. Probability of F, that even number occurred, is 1 by 2. So this is basically 2 by 6. So this is basically 1 by 3. So when we consider that probability 2 occurs, that probability is of 1 by 6. But when we consider that even number has occurred, then the probability of occurrence of 2 has changed. So this is this concept that how one event has an impact on occurrence of other event. This concept was defined or was considered by this concept, conditional probability. So general multiplication rule was also discussed, that if I consider a1, a2, an that are basically element of B, with probability of their intersection to be greater than 0, then probability of intersection of AI can be calculated or evaluated by by using the concept of conditional probabilities, by this formula, that probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2, and so on, probability of AN given A1 intersection A2 intersection AN minus 1. So this was a general multiplication rule. If these conditional probabilities are given, then we can by making use of these conditional probabilities, we can calculate the probability of their intersections. So apart from this, theorem of total probability, so this was like, if I consider b1, b2, bn and so on, pairwise disjoint events, means there the intersection of bi and bj is empty, with B to be equals to union of Bi, then for any event A. So let us consider that this is an event A. Now what I'm doing, I'm just partitioning this B1, B2, this be an event B1, this be an event B2, dash dash dash. So these are the BI's events. So what I'm doing, I want to find the probability of A intersection B. So it will be the summation of probability of A given Bj into probability of Bj. So this was the theorem of total probability. Now through these concepts only there comes a Bayes theorem, that is, now if we are considering that B1, B2 are again pairwise disjoint event such that their union is whole sample space, then, and also we are given the prior probability of the events Bi to be greater than 0 for all i's, then for any event A, if we want to find out the probability of Bi given the event A, then probability of Bi given A is given as probability of A given Bi into probability of Bi divided by the whole probability of Bi, which is, this is basically, this is nothing but this is probability of A. So which is written as the theorem of total probability, this the expression in the uh, denominator has been arrived. So this was basically the Bayes theorem. Now apart from this, independence of event, like if I have two events, then when those two events are said to be independent, so any two event A and B are said to be independent if probability of A intersection B is equals to probability of A into probability of B. Or intuitionally we can say that probability of A given B means that the probability that A occurs given B has already occurred is equals to probability of A. This implies, what it implies, that B has no effect on the occurrence of A. So basically, B has no effect on occurrence of A. That is probability. This conditional probability is equals to the original probability, that is probability of A. Then we will say that A and B are independent event or statistically independent event. So these are the two definition by which we can say that A and B are statistically independent. So mathematically, this formula is used in order to see whether A and B are independent or not. This we can also use this, but more this formula is used. So apart from this, the concept of random variable was defined. So I am audible to you all?
Yes, ma'am.
Okay. So apart from this, this random, the concept of random variable was defined. So if I consider omega bp be a probability space, so basically I'm having this whole set and this sigma algebra and p be a probability function. So this is a probability space. Now I'm considering real the set of real numbers r and c. Here this c is a class of subsets of r, okay, and which is sigma algebra. So we are saying that RC is a measurable space. We are saying RC is a measurable space means R is the whole sample space, and C is a class of subsets of R which forms a sigma algebra. So this is a measurable space. Then what we are doing when we are defining a function from the sample space omega b to RC such that, so basically what X is doing, X is taking elements from omega, means the sample space. So basically X is taking events and it is assigning those event a real number. So so when this function is said to be a random variable if for any b in C. So if I take any b from this sigma algebra, then its inverse image means the X inverse b. So the inverse image will come here. So this inverse image should belongs to the sigma algebra of this sigma algebra, which is defined in this measurable space omega b. So when this condition holds, then we will say that X is a random variable. So why we are defining this notion of random variable? Because random variable is important because we cannot always deal with the like events. We cannot always state the events and do the thing. So basically we are assigning a real number to the events to make the further study more like more precise, and also it is like easily handled. We can easily handle those situations when we are dealing with a real number as compared to we are considering the uh, the events in a different way. So also there is a if and only if condition for function to be a random variable. That is, if I consider this function x omega b to rc, then we say that x is a random variable if and only if anyone, if I consider any one of these conditions, then if any one of this condition is satisfied, then I will say that x is a random variable. So what basically this condition is. So if I'm explaining one of these, then other can be like easily followed up by this. So what is this? So basically x is a function from omega to r. So it is taking events and giving a real number. So omega such that x omega is less than. So basically what this set is omega, that is element from the sample space such that where this function is sending this element from the sample space. Now this s omega is belonging to minus infinity comma a. So if I'm considering this thing x omega is less than is equals to a, so basically it is going in real number, so a is a real number. Now x omega is less than is equals to a, what it means that it belongs to minus infinity to closed a. So if I'm considering any of the event here and this function is sending those event such that it belongs to this type of interval for any a in r. Now a can be anything in r. So if such thing happens and this basically this set is in b, which is basically here this class, which is a sigma algebra. So if this is in b, then we will say that x is a random variable. Similarly, if this condition holds, this implies that omega belongs to this omega such that x omega belongs to minus infinity to open a. Similarly, we can also do for this omega belongs to omega such that this random variable is sending the elements such that the image belongs to closed a to infinity. And similarly, we can say about this that omega and omega such that x omega belongs to open a to infinity. So if any of these condition holds that such that this stat belongs to the Borel this sigma algebra B, then we'll say that x is a random variable. So this basically is a theorem, and it came by using the definition of the random variable. So apart from this, there was another theorem that if x is a random variable which is defined on the probability space omega bp, then this also induces another probability space which is rcq. So what basically is happening here? So what we have done, first we have considered the whole sample space. Then we have defined, first of all in all the lectures, first of all what we have done, we have defined probability function. So we have defined probability function which is taking the events to the real number, or we can say to 0 1. Basically the probability is going to what, from 0 to 1, it takes value from 0 and from 0 to 1 in close to 0 1. So we have defined a function from omega to r, which is basically a probability function. Then by the concept of random variable, what we have done, we have uh, again defined a function on omega which is taking the events to real numbers. Now these real numbers can be anything. Now random variable can take any value on the real line. Now these two functions are defined from omega to r, and other function that is x which is omega to r only. Now from these two functions there is another function. So if I take this, the inverse of this function, then this will be x inverse, and here from this to this it is basically p. So if I consider the composition of these two functions, it will be px inverse. So that will be a function from R to R, which I have defined this. So by using these two functions, there is another function which is defined from R to R, which is nothing but Px inverse, which we are calling as this Q. So this QB is nothing but P of X inverse B, which is nothing but probability that omega, such that omega X omega is in B. So basically this function is taking values from the original functions x inverse and p, and we are defining this q, and because this q is defined from r to r only. And here we are considering this to be a domain. This is a ring. So here this r, c is a sigma algebra, and q, this is again a probability space, which is already proved in the lectures that this is again a probability space basically, and this is a probability function. So in order to explain it a little better, in a better way, I have considered this example. So let us consider this tossing of a coin. So what are sample spaces? Our sample spaces, we are getting head or tail. So if we want to assign a probability function to it, so we know that we are considering a fair coin. So we are considering a fair coin. So the probability of appearance of head will be 1 by 2, and probability of appearance of tail is 1 by 2. Now, how can we see it in a different scenario by using the concept of random variable? So let us consider x be a random variable. So which counts a number of heads. So what it is counting? It is counting the number of heads. So since the random variable is defined from omega, so it will take domain to be the elements of the omega. So which is head or tail. So the random variable x will give the event h to be value 1 because there is one head, and in the this event tail there is no head, so it will give value 0. So basically this the function x is defined, random variable is defined. Now how this q come into the picture? So if I consider qb, so qb will be probability of x inverse b, which is nothing but probability that omega, such that x omega is in b. So let us consider in a different way, that q of 1. So basically q is a function from r to r. So I'm considering here the value 1. So q of 1, so which is what probability that x inverse 1. What this x inverse 1 is? Omega, such that x omega is equals to 1. So what are those events which are sending, which the random variable is sending to 1? Which are these events? That is simply singleton h. So this is nothing but probability of singleton h, which is 1 by 2. And we represent this whole notation by probability x is equals to 1. Now q again, apart from this one, we have also considered q of 0. So what this q of 0 is? Probability x inverse 0 means probability omega, such that x omega is equals to 0, means those events the random variable are sending those events to 0. Which are those events? So which are those events which random variable is sending to 0? This is nothing but singleton t. So it will be probability of singleton t, which is 1 by 2, and we will represent it as probability x is equals to 0. So basically probability x is equals to 1. What it means? That probability of omega such that x omega is 1. So we are finding the probability of those events which the random variable is sending to 1. So this is basically the meaning of this probability x is equals to 1. When we are writing probability x is equals to 1, we are basically finding the probability of those events. The random variable is sending those events to 1. We are finding the probability of those events basically. So this is basically how the random variable and the probability functions are connected. So after this, the concept of random variable, this cumulative distribution function was defined. So which is basically was probability that omega such that x omega is less than is equals to x, and if we want to write it in the function of in the like notation of the random variable, then it is probability x less than is equals to x. So basically how you can see that x is a random variable, then it can take value 0, 1, 2, 3, and like it can take value from real numbers. Now what is the probability that x is equals to 0? We will be discussing it later. We will find this and all these things. And I am considering probability x less than is equals to x, what I'm considering that what is the probability that the random variable um, what it means that probability omega such that x omega is less than is equals to x. So we are finding basically the probability of this event when we are writing this. So this is basically a distribution function we are calling. Now this is the cumulative distribution function. This is defined for a random variable. Now there are some properties which this distribution function holds. So what are these properties? That if I want to find the limit, so limit x tends to minus infinity. So when x tends towards minus infinity, where this fx is going towards 0. And when x tends towards plus infinity, this fx is going towards 1. And also this fx is increasing function. So x1 less than equals to x2, fx1 will less than equals to fx2. Other than this function is also right continuous. Means the right hand limit of the right hand, this function is right continuous, means the right hand limit of the function will be equals to the functional value of that point. So this is right continuous, so which can be calculated using this formula that limit h tends to 0, fx plus h is equals to fx. So if this relation holds, then we will say that fx is right continuous. So these are the four basic properties which the cumulative distribution function holds. So if you want to find out that any you have given that this is whether you want to check that this distribution function, this is a function and whether it is a distribution function or not. So you will be checking these four properties. If a function follows all these four properties, then we will say okay, this is a cumulative distribution function. So apart from this, these random variables are of two types basically. So only one type has been discussed in week 2. So I will be concerning with only this type, that is discrete random variable. So a random variable which is defined on a probability space, this will be called a discrete random variable if there exists a countable set E contained in R such that probability X in E is 1. So we can also understand it in a way that if I'm considering a random variable x, I'm considering this from the whole sample space to R. Now if this the range of this random variable means the random variable can be anything. When the range of random variable x, range you understand na? What the functional value in what are the functional values of x are there. So we will call that x, the range of x. So this when the range of this x is at most countable, means it can be the range can be finite. So it can be finite, or it can be countable. So it should not be uncountable. So if the range is countable or finite, then we'll say that this random variable x is a discrete random variable. So in discrete random variable, there is a concept of probability mass function. So basically, this is nothing but if we want to find out the probability, like x is taking values, and if we want to find out the probability at x is equals to 1, probability at x is equals to 2, if we want to find out, then we'll say that probability x is equals to x, where x is varying basically. So this we call it as probability mass function. Now, this probability mass function also have some properties. Since we all know that probability cannot be negative and it cannot be greater than 1, so this is obvious that pxx, that is probability x is equals to x, is always greater than or equals to 0. And also, if I consider the summation of this px, that I'm taking the total probability, then this total probability can be, sorry, it will be equal to 1. So these are two properties of probability mass function. So if any function is given to you and they've asked that whether just tell me whether it is a probability mass function or not, so you will consider these two conditions, and if these two conditions are satisfied, then we will say that this function is a probability mass function. So this was basically has been covered by the professor in week 2 lectures. So on the basis of these concepts only, I will be addressing some of the questions. So if anyone has any doubt in these concepts of anything, then you can ask. So if there are no doubts, then I will be moving forward. So I hope this screen is visible to you.
Yes, ma'am.
Okay, okay. So there was some
Yes,
glitch.
ma'am.
Yeah. Okay, I will be now going towards the questions. So you people also just try to solve these things with me, and then it will be interesting for you also to the class will be interactive. So let me read it first. So if so the question says if an aircraft is present in certain area, a radar detects it and generates an alarm signal with probability 0.99. So you people, as we have already discussed about the conditional probability and all these things, so just think in that way, then you will be able to understand the problem and all these things. So so what they are saying that if an aircraft is present in certain area, and so we are having this one event that aircraft is present in certain area, and a radar detects it and generates an alarm signal with probability 0.99. So there we will consider two events. Let us consider, let A be an event that aircraft is present. So there the complement will be that aircraft is not present. So basically this be an event A, and B be an event that alarm is generated. So we are considering these two events. So what it is saying, if an aircraft is present in an area, so we are given that the aircraft is present. So uh, and generates an alarm signal with probability 0.99. So basically what this probability 0.99 is, so this is probability what is given that aircraft is present in certain area. So what is given, the event which is given is A. So aircraft is present, then radar detects it and generates an alarm. So alarm is generated. What is the probability that alarm is generated? this is the event B. So what it is given 0.99 to be probability of B given A. So they are saying that the aircraft is present in an area, means they are giving that the aircraft is present, but and they are giving the probability that the signal will be generated or the alarm will be generated, then the probability is 0.99. So basically this is probability B given A. Apart from this, if an aircraft is not present, so they are giving that aircraft is not present. So what is the probability further they are giving, that what they are giving, that aircraft is not present. So this is basically a complement here. So aircraft is not present, then the radar generates an alarm with probability 0 point. So alarm is again generated. So probability of B, given that the aircraft is not present, this probability is given as 0.10. So these two probabilities we are having. Now again, what they are asking, we assume that an aircraft is present with probability 0.05. So the event A is aircraft is present. So what they've given, that probability of A is equals to 0.05. Now what they're asking, what is the probability of no aircraft present and a false alarm? What they are saying, see here and is given, and and basically means for the intersection. So what they are asking, that probability that no aircraft means A complement. So A complement intersection, there is a false alarm. False alarm means, so false alarms, what does this false alarm will mean? So what they are asking, that there is no aircraft present and there is a false alarm. So they are basically asking probability of A complement intersection, that there will be alarm generated. Basically they are saying false alarm, but alarm is generated. So they are asking A complement intersection B. This is in question. So here we have given that what is probability of A, probability of B given A complement, B given A, and we have asked that probability of A complement intersection B. So how this can be calculated further, we can use the formula for the conditional probability. So let me, so what we know, that probability E given F is equals to probability E intersection F divided by probability of F. So sorry, so this is basically a conditional probability. Now what they have asked about probability A complement intersection B, and we have probability B given A complement. So we can write this formula for probability B given A complement. So what this will be, this will be probability B intersection A complement divided by probability of A complement. So since we know that probability of A is 0.05, it was given that probability of A is 0.05. So probability of A complement will be what? Probability of A complement will be 1 minus probability of A, which will be 1 minus 0.05. So it will be 0.95. So, and probability of B intersection A complement we need to find out. And what is probability of B given A complement? Which is 0.10. So, with this is 0.10. So, it will be what? Probability of B intersection A complement will be, probability of B intersection A complement will be probability of B given A complement into probability of A complement, which is nothing but I'm just cross multiplying these terms. So it will be probability B intersection A complement is equals to probability of B given A complement into probability of A complement, which is nothing but what it is, 0.10 into 0.95. 0.10 into 0.95. So it will be 0.095. So this will be the probability which has been asked in the question that what is the probability that there is no aircraft present and a false alarm. So the main thing in understanding the question is to understand the language of the question, that what they have given and what they are asking. Then you will be done by using the formulas. So I hope this is clear to all. So is this clear?
Yes, ma'am.
Okay. So now we will move forward towards the second question. So the question is saying, suppose you enter a chess tournament where your probability of winning a game is 0.3 against half the players, and zero point 0.4 against the quarter of the players, and zero point 0.5 against the remaining quarter of the players. So so if I have I have players, then half of the players, against half of the players, the probability of winning is 0.3. Against the quarter of the player, the probability of winning is 0.4, and against the remaining quarter it is 0.5. So how to write it in a in a conditional probability sense? So first of all, let us consider the probability of, so the event of winning. So let C be event of winning. So this is that what is the probability of winning. So this is an event of winning we are considering. Now what they are asking, that the probability of winning a game against half of the player. So first of all, let us consider event AI. So this is uh, event of uh, getting, event of getting players of type I. So there are three types of player. Type 1, which is half of the player, we are saying that these are the player of type 1. Quarter of the player, we are saying this is a type 2, and remaining quarter we are saying a type 3. So we are saying that AI is an event of getting a player. First of all, we how what is the probability that the player will be of type 1 or type 2 or type 3? What we are considering for that, this event AI is event of getting a player of type I. Okay. So and C is the event of winning. So first of all, we'll consider, so what will be this 0.3, 0.4, or 0.5? So basically this is probability. What they are saying, that winning a game against a half of the players. So that is the players of type 1. So probability of winning, and they are given that the players are of type 1, C given A1. This will be 0.3. Probability of C given A2. This is probability 0.4. Probability that C given A3. This is 0.5. So basically these are the probabilities of these are the basically conditional probabilities. Now A1 is a type 1 player. Type 1 player means half of the players. So probability of getting half of the players will be 1 by 2, and probability of getting quarter of the players will be what it will be. So probability of getting quarter of the players will be 1 by 4, and other quarter also probability of A3 will be 1 by 4. See, because we are considering whole to be 1, and see, whole, anything whole we are considering to be 1. So the probability of getting half of them will be 1 by 2. A probability of getting this quarter will be 1 by 4, and other quarter will be 1 by 4. Actually we are calling it as half or quarter, we are saying the same thing only. So these are the probabilities. Now what they are asking, you play a game against a randomly chosen opponent. Suppose that you win, so they are consider that you won the game. Now what is the probability that you had an opponent of type 1? So what they are asking basically, that probability that the opponent was of type 1, given that you have won the game. So you have won the game, the event was C, and you are getting the player of type 1 was an event A1. So basically they are asking probability of A1 given C. So this is in question. So now again what we will do, we will use a Bayes theorem. So what Bayes theorem says? What is Bayes theorem? So this basically says that probability of A1 given C is equals to probability of C given A1 into probability of A1 divided by probability of C given A1, probability of A1 plus probability of C given A2, probability of A2 plus probability of C given A3, probability of A3. So which is the denominator is what? Nothing but it is basically probability of winning. This is probability of C only, which we are considering in the denominator. So probability, we will just place the values here, that what is probability of C given A1. So probability of C given A1 is 0.3. So this is basically, so this probability of A1, sorry, probability of, yeah, that was correct. A1 given C is equals to, so what was there? Probability of C given A1. So C given A1 was 0.3 into probability of A1, which is 1 by 2, that is 0.5. So 0.3 into 0.5 divided by, again 0.3 into 0.5 plus what are the other things? Probability of C given A2. So which is 0.4. C given A2 is 0.4 into probability of A2 was the quarter player selection. So this was 0.25, which is 1 by 4. Again, the probability of C given A3 is 0.5. So it is 0.5 into 0.25, that is probability of A3. So this will be 0.15 divided by again 0.15 plus 0.1 and that's what it will be. So just calculate it and just tell me what the answer is coming. So someone is calculating or not? Please let me know. If you're calculating, then let me know. If you're not, then let me know. So it will be 0.15.
0.
Yeah, what?
0.15.
0.15? No, we have to divide it, na? 0.15 divided by this
Oh, yes,
quantity.
ma'am. It is 0.4.
Yeah, it is 0.375 in the denominator, so it will be 0.4. So yeah, correct. So this is basically the probability of A1 given C. Now, another thing also in the question, which is asking that what is the probability of winning? So probability of winning, basically what they are asking, that what is probability of C? So if I consider the theorem of total probability, then this is nothing but probability C given A1 into probability of A1 plus probability of C given A2 into probability of A2 plus probability of C given A3 into probability of A3, which is nothing but the denominator here, which we have used, which is nothing but 0.375. So this will be the probability of winning. So I think this is like clear to you. The main thing is making the events, which we are considering, that how AI we are making, how C we are making, and how we are using it in formula. So this is the main thing to understand the question. Then we can follow up by the formulas which are already given. So I will move forward towards the next question. So yeah, this is a question for a cumulative distribution function. So we need to check whether a function which is given in the options, whether they are cumulative distribution functions or not. So first I will consider the first function. So what this function is, fx is equals to, so is, so fx is equals to 0 when x is less than 0. It is 0.5 if x is greater than equals to 0 and less than 1, and it is 1 if x is greater than equals to 1. So basically we need to check whether this is a cumulative distribution function or not. Now for that we need to check four things. If any one of them uh, if any one of the of any one of them fails, then we'll say that this is not a distribution function. So first we will check that limit x tends to infinity fx should go towards 1. Limit x tends to minus infinity fx should go towards 0. And x1 less than x2, then fx1 should less than equals to fx2. That is, the function should be increasing. And also what? Limit h tends to 0, f x plus h. This should be equals to f of x, means the right continuity. So these four things we need to check in order to say that this is a distribution function. So we'll check this first thing. Okay, let me plot this function first. So if I plot this function, so if I plot this function, then it will be easy to see. So if I plot this function, let's see, say when x is less than 0, this function is 0 only. So for all the, so here this is x and here this is fx. So for all the values which are less than 0, this function is 0. So basically this line is coming, this line is the, when the x is less than 0. Okay, now when the function is between 0 and 1. Now I'm considering here this is 1. Okay, and this to be 0.5 and this to be 1. Now they're saying that when x is greater than equals to 0 and when x is less than 1, means this domain, they are saying for this domain where the function is going, the function is 0.5, and they're including this point 0 also. So here this 0 is not included, but here it is included. So it is 0.5 up till 1, but 1 is not included, so it will not be there in 1, so it will be before, up till before 1. Now when x is greater than equals to 1, it is 1, the function is 1 here, so it is starting from here, then it is constantly 1 for all x. So by watching this function, if x is tending towards minus infinity, we are seeing this function is going towards 0. Function is going towards 0. When we are seeing this is continuously going, so when we are seeing that when x is going towards infinity, this function, where this function, the functional value is 1 only, so the function is going towards 1. So these two conditions are satisfied by this function. Now what other thing, when x1 is less than x2, fx1 should be less than equals to fx. Basically the function is increasing. So if you see the graph, when x is increasing, always the function is increasing only. By the graph we can already see that the function is increasing only. For any x1 less than x2, the functional values is always greater than, because if the function was like this, increasing then decreasing, then the function will be, we call that here the function is increasing but here the function is decreasing, but here we can say that the function is increasing. So this is clear from the graph only. Now, what about the right continuity? So let me explain about this right continuity, what this will say. So you have to take next slide. See, okay, there is one thing to notice here. that yeah, so we need to check the right continuity of the function. So before the when this function is less than 0, then it is continuous. So there is a point of discontinuity at 0, and there is a point of discontinuity at point 1. So we need to check these 2 points for right continuity. Okay, so for right continuity, so we need to check. So we need to check at points x is equals to 0 and 1. So for x is equals to 0, if I consider, so limit h tends to 0, f of 0 plus h. So what it will be? F of 0 plus h will be what? What is 0 plus h? When x is greater than 0, the functional value is 0.5. So it will be constant function, so it will be 0.5 only, which is 0.5 because there is no term of h here, so it will be 0.5. And what is f of 0? What is the functional value here? F of 0? F at 0, the function is taking value 0.5, so it is 0.5. So both the values are equal. So it is right continuous at point 0, which implies at 0 it is right continuous. Now for we'll consider x is equals to 1. So limit x h tends to 0, f of 1 plus h. So what it will be? Limit h tends to 0. What at 1 plus h, what the function is? See, when x is greater than equals to 1, the function is 1. So whenever x is greater than equals to 1, the function will take 1 value. So since here in the this domain 1 plus h is given, which is already greater than 1. So f of 1 plus h will be 1 always. So which is equals to again 1 because there is no h term here. And what is f of 1? The function is taking at value 1, it is taking 1, so it is 1 only. Again these are equal, which implies at 1 it is right continuous. So what we conclude, that all the conditions are satisfied. This implies that f is a distribution function. Okay, so we are done with this first part. So this is basically a distribution function. Now we will consider the second part, B part. So for B part, what the function fx is? So how it is defined? 0 when x is less than 0, and 1 when x is greater than equals to 1. Sorry, greater than equals to 0. Okay, so this is the function again. So what we will see, first of all, let me just draw the graph. So how the graph is, when x is less than 0, the function is 0. So the function is taking 0 value, but at 0 it is not 0. So it is taking the 0 value. Now when x is greater than equals to 0, it is 1. So basically it is 1 when x is greater than equals to 0. So it is 1. So here it is x, and here it is taking 1. This is 0. So we are seeing that when x is tending towards minus infinity, the function is going towards 0. And when x tends towards infinity, where fx is tending? Where fx is tending towards 1 only. Fx is 1 for every value of x which is greater than 0. So if x tends to infinity, fx is going towards 1. So first two conditions are satisfied. Now we can also see the function is increasing. Since the functional values are always greater, for when x is increasing, the function is either constant or increasing. So this is also an increasing function. So increasing function. So now last condition, which is the right continuity. Now the continuity breaks at the point 0 only. Otherwise the function is continuous. So we will check at point 0. So at x is equals to 0, we will check. So what it will be, limit h tends to 0, f of 0 plus h. Now what it will be, limit h tends to 0, f of 0 plus h. What will be the value? Since x is greater than equals to 0, the functional value, the value of the function is 1. So it will be 1, and it does not depends upon h, so it will be 1 again. Now, and the functional value f of 0 is, this is nothing but this is 1 only. So this is again, this implies it is a right continuous. So this implies that f is a distribution function. So this function is also a distribution function. Now we'll consider the third one. So now in this you will be see the other formats also. So what the function is, fx is equals to 1 upon pi tan inverse x minus 1. So fx is equals to 1 upon pi tan inverse x minus 1, and x is from minus infinity less than x less than infinity. Okay, so what we need to check first of all, limit x tends to infinity 1 upon pi tan inverse x minus 1. So since this is basically a continuous function, so limit will go inside, or we can say that when x tends to infinity, where the tan inverse x goes, see, if I make this graph of tan inverse x, so it is like, so it is like, so here it is pi by 2 and here it is minus pi by 2. So when x is going towards infinity, when this x is moving towards infinity, where this fx is going, fx not fx, this is tan inverse x basically. So this is not fx. So this is a graph for tan inverse x. So when x is going towards infinity, tan inverse x is going towards pi by 2, because the function is going towards pi by 2. Now, since tan inverse x is going towards pi by 2, where this limit is going? So, since the tan inverse x is going towards pi by 2, so this is 1 upon pi here, and tan inverse x will go towards pi by 2 minus 1. So, this will get cancelled, and this will be 1 by 2 minus 1. This is minus 1 by 2. So, which is not equals to 1, which should be equal to 1 for f to be a distribution function. So, what this implies? This implies that f is not a distribution function. You can also apply the limit x tends to minus infinity, then you will be able to see that again the function is not going towards 0. This whole fx is not going towards 0. So you will say that this function is not a distribution function by that argument also. However, the function is increasing. This tan inverse x is increasing, but we can also check the behavior of this function also about the increasing. But this argument is enough to say that this function is not a distribution function, because as x is going towards infinity, the function is not going towards this, fx is not going towards 1. So we'll say that f is not a distribution function. So this is not a distribution function. Now the last one we'll see. So the last one is the D part. How the fx is defined? Fx is defined as, so let me see. So it is defined as x0 when x is less than is equals to 2, 0, sorry, and e to the power minus x square plus e to the power minus 2x when x is greater than 0. So we need to check that where this function is going when x tends to minus infinity and when x tends to infinity. So see, this function is 0, 0 when x is less than equals to 0. So from there, limit x tends to minus infinity, the function will go towards 0, because the function is 0 for all x less than equals to 0. So it is basically, if I consider this function is like 0 for all x less than 0. So as s tends to minus infinity, the function is going towards 0. So there is no doubt in that this will go towards 0. But when limit x goes towards infinity, so where this e to the power minus x square plus e to the power minus 2x goes. So when this goes towards infinity, this is basically nothing but what? It is basically limit x tends to infinity 1 upon e to the power x square plus 1 upon e to the power 2x. Basically, I'm considering the positive powers, so I have taken it as the reciprocal. So when x goes to infinity, since the numerator there is no problem, in the denominator when this x goes towards infinity, e to the power x goes towards infinity again, and 1 upon infinity goes to 0. So this term goes to 0, and same with this, when x goes towards infinity, e to the power x again goes to infinity, and 1 upon e to the power x, e to the power 2x goes to 0. So this function is again going towards 0. So this is which is not equals to 1. So this implies not a distribution function. And also you can also give it, this is also an argument to say that this is not a distribution function. Other than this, you can also see that this function is not an increasing function. This function is a decreasing function, not it's increasing function in the whole domain. So we'll say that this function, by that argument also we can say that this function is not a distribution function. So these are the four functions which we have considered in order to see that whether they are distribution function or not. So this one is also not a distribution function. So I hope the concept that how we need to check that the function is distribution function or not, that thing is clear, that how this definition has been applied to the real when the distribution function is given. I hope by these example that concept is clear. Okay, so we'll move toward the fourth question. So, in a town, 30% are businessmen, 20% are in academics, 50% are in other professions. So, the probability that an innovative idea is developed by businessmen, academicians, or other professional is respectively 0.7, 0.8, 0.3. So, basically, we are considering uh, we are considering that what the person is, whether it is he or she is a businessman, academician, or a other professional, and whether the idea has been developed, innovative idea has been developed or not. So I'm considering in event A that innovative, or I will say just idea. There's no need to say this innovative. So idea is developed. Okay, and I am considering B to be an event that the person is businessman. Uh, uh, okay, C to be an event. Okay, let me name it in a different way. Idea has been developed. I will say it by I. Okay, so it will be easy to conclude that what we are actually doing. And A to B, that the person is academician, and OBA, that the person is in other profession. Okay, so what they are saying that in a town 30% are businessmen. So probability that a person is a businessman. So probability that a person is businessman is equals to 30%. So it will be 0.3. Now probability that a person is in academics. So it will be what? So person is in academics, it will be 20%. So it is 0.2. And probability that he or she is in other profession, that it is 0.5. Now that is 50%. Now what they are saying, that the probability that an innovative idea is developed by a businessman. So what they are saying, that innovative idea is developed basically. So this is a given event and it is developed by a businessman. The probability is given as 0.7. So basically what it is given that the innovative idea has been developed already. So given event is that innovative idea is developed. Now it is developed by a businessman. That probability is 0.7. So probability B given I is 0.7. The innovative idea is developed by businessmen. The probability that an innovative idea is developed by academician is 0.8. So probability that the innovative idea is being developed by academician is 0. What 0.5 0.8, sorry, 0.8. So it will be 0.8, and probability that the innovative idea has been developed and it is developed by other person from other profession, so it will be 0.3. 0.3. Now, what they are asking that a person, the randomly chosen person from this group is found to have generated an innovative idea. What is the probability that he or she is an academician? So a random person is chosen, and it is found that he or she has generated the innovative idea. But what they're asking that what is the probability that she or he is an academician? So what they are asking that probability that he or she is an academician given that innovative idea has been, what is the probability that he or she is an academician? Okay, so they have asked, wait a minute. Okay, maybe there is some mistake I've done. So the probability that an innovative idea is developed by a businessman is 0.7. So basically what I have done, I have just written the probabilities to be the in other way, which is it is basically that probability that the innovative idea has been developed and a person is an probability that innovative idea is developed, person is a businessman. I've written it in a wrong way. So it will be probability I given B. So basically what they're saying, let me explain it again, that what they're saying, that the probability that innovative idea is developed by a businessman. So the person is businessman, and the probability that the innovative idea is developed is 0.7. So basically it is in a other way. So let me correct it here also. So it will be I given A, and it will also be I given O. So now what they're asking, that a randomly chosen person from this group is found to have generated an innovative idea. So the innovative idea is basically generated. The innovative idea is generated, but what they're asking, what is the probability that that person is an academician? So basically we will use the Bayes theorem again. So probability that A given I, it will be probability that I given A into probability of A divided by probability of I given A into probability of A plus probability of I given B into probability of B plus probability of I given O into probability of O. So it will be, since the values are given here, so what are the values? 0.8, which is equals to 0.8 into, what is the probability of A is 0.2. 0.2 divided by 0.8 into 0.2 plus I given me 0.7 into 0.3. So it is 0.7 into 0.3 plus 0.5 into 0.3. 0.5 into 0.3. So it will be like 0.16 divided by 0.16 plus 0.21 plus 0.15 then it can be further calculated. So what the answer is coming? So it is basically 4 by 13 we are getting. So this is the probability for that. So okay, we'll move forward for the next question. Um, yeah. So what it is saying that consider the following experiment. You draw a square. So you draw a square of width 1 foot. So we draw a square. So we draw a square whose width is 1 foot. Okay. Now, inside this square, you inscribe a circle of diameter 1 foot. So basically, we are inscribing a circle inside this square. So it is the circle which is not looking like one. Okay. So it is the circle we are inscribing, and this diameter of the circle is again 1 foot. As we can see, also since the square is 1 foot wide, so it will be 1 foot. Now the circle will just fit inside the square. Okay, you then throw a dart at the square. So we are throwing a dart at it. We are throwing dart, so we can throw it at any point in the square. So we can throw it. So what they are asking, that and also you this the way which we are throwing, so it is equally likely to fall at any point on the square. So if we are throwing it at one point, then they are equally likely that it can happen to other point also. So this the all the outcomes are equally likely basically. So what is the probability that the dart falls inside the circle? So what is the probability that it will fall inside the circle basically? So this is nothing, because what the formula will be used as a favorable number of outcomes, basic formula, divided by total number. So total number of outcomes will be, it can be anywhere inside this square, so which is basically the area of the square. And the favorable outcomes is that the dart is there at the circle, yeah, on the circle. So the number of favorable outcome will be the area of the circle. So this is nothing but will be equal to area of circle divided by the area of square. So area of the circle will be nothing but pi r square, and area of the square will be what, since this is the diameter, so area of the square will be d into d, which is basically the diameter. So pi r square, and diameter is 2r, so it will be 2 into r into 2 into r. So this r square will get cancelled, so there is no role of the radius or 1 foot. So this is pi by 4. So this will be the probability the dart falls inside the circle. So this is basically we are saying that this will be the ratio of the area of the circle and the square. Okay, so yeah, we'll go towards the next question. So here an urn contains 10 red balls and 8 blue balls. So here there is an urn which contains 10 red balls and 8 blue balls. Now, 3 balls are selected without replacement. So, we are selecting 3 balls. So, basically, we have these 3 balls we are selecting. Okay. So, we are selecting this, and without replacement, we are selecting here. So first of all, we'll count the total number of possibilities. So, if I'm selecting the first ball, then total number of how many total number of outcomes are there? So, total number will be 18. I can select it from whole 18 balls. Now for the second one, these are the total number. So these are 18 possibilities, and for this there are 17 possibilities. For this there are 16 possibilities. Now what they are saying, find the probability of the colors of balls are in sequence blue, red, blue. So here it is blue, here it is red, and here it is blue. So for selecting this blue, how many possibilities? Favorable 8. There are 8 possibilities. And for this red one, how many possibilities are there? For this red one there are 10 possibilities. And for this, again this blue one, there are 7 possibilities. So we can write it as 8 into 10 into 7. divided by 18 into 17 into 16, which can be, which we can find out, and it is basically 35 by 306. So this is basically the probability. And also we can do it in another way, like this is the basic way, this is the basic probability, and by using this concept of the general multiplication rule also we can do it. Now for that we have to consider what, so for that alternatively how we can do it. So all the, so alternatively how we can do that, so let us consider pi to be blue ball selected on ith draw. So there are basically three draws. So we are considering bi to be blue ball selected at ith draw and ri to be red ball selected on ith draw. Okay, so what we basically want to find, we want to find probability that at first draw there is a blue ball, so basically b1. At second row intersection, there should be a red ball, and at third row there will be the blue ball. So we are basically finding out the B1 intersection R2 intersection B3. So since this is intersection, and by general multiplication rule, what we can write it as probability of B1 into probability of R2 given B1 intersection B3. Okay. Oh, no, sorry. So probability of B1 and probability of, again we are considering the next event, so R2 given B1 into probability of B3 given B1 intersection R2. So these events we are considering. So probability of P1 means at first draw we are getting, at first draw we are getting a blue ball. So there are how many blue balls? There are 8 blue balls, and we are selecting this 8 blue balls from 18 total. So 8 by 18 this will be, and what this will be, probability that R2 given B1. They are saying that what is the probability that at first draw there is a blue ball and at second draw there will be red ball. So since at first draw there, since the first draw has already happened, so the number of outcomes for the first draw, so total number of possibilities for the second draw will be 17. So the total will be 17. But and the probability of getting a red ball, so there are total 10 red balls, so this will be 10 by 17, and into this is probability that at first draw there is blue ball, second draw there is third this red ball, and third draw there is again a blue ball. So here the total possibilities is two draws that already happened. So there are 16 total possibilities which we can through which we can draw, and at third point there is blue ball. What is the possibility for that? That will be 7. So this is again the same thing, 8 by 18, 10 by 17, and 7 by 16. So this is basically, this is again 35 by 306. So this can be done by using this multiplication rule also. Okay, so we will be moving forward for the next question. Okay, so they're asking that which of the following is not a valid probability mass function of a discrete random variable. So basically, we'll consider here whatever the question is. We will consider all the properties, the two properties of probability mass function, which a function should satisfy to be a probability mass function. Also, this probability mass function is, in short, we call it as PMF. So I will be saying it as PMF. Now, okay, so there are two properties that a PMF should follow. That is, probability x is equals to x. Whatever the x is, it should be greater than or equal to 0. Second one is that summation probability x is equals to x. We are summing it over x, and this should be equal to 1. So these are the two properties we need to check in order to say that the function is probability mass function. So let us consider the first function. First function, which is probability x is equals to what this function is. p q to the power x, p into q to the power x, and p is greater than 0, q is less than 1. So p is greater than 0, q is less than 1. P is equals to 1 minus q. P is equals to 1 minus q. Okay. And x is varying 1, 2, 3, and so on. So these are basically conditions. So there are two ways by which you can deny. You can deny both the conditions for this function. So let me consider the first one. For us to have this p as a probability mass function, this should be greater than 0. Since in the question it is given that p is greater than 0, so this quantity will be greater than 0, no doubt. But what about q to the power x? Now q is less than 1 and p is 1 minus q. So in particular, if we consider, since p is q is less than 1 and p is since p is 1 minus q and this q is less than 1, so this whole quantity, so let us consider q to be minus of 2. Okay. Now, if I'm considering q to be minus 2, then none of the condition is violated here. Here, p is greater than 0. And if I consider q to be minus 2, then what will be p? So, p will be 1 minus minus 2. So, it will be 1 plus 2, that is 3, which is greater than 0. So, this condition is done. Q should be less, q is minus 2, which is less than 1. So, this condition is also done. And so these two conditions are already given, which is done by consideration of this. Now if q is minus 2, then if I'm considering probability x is equals to 1, if I'm considering this will be p into q, because here this is 1, so p into q. So this will be, what is p we are considering, we are able to find out that this is 3, and q is minus 2, so it is minus 6, which is less than 0. So this condition is violated, that probability x is equals to 1 and probability cannot be negative. So this is not a PMF directly from here. We can also see the summation part also, that probability, that summation p q to the power x, where this is running from 1 to infinity. Now here this is equals to p summation q to the power x, where x is going from 1 to infinity. Now, when we sum this series, then this will be p into summation 1 to infinity. This is q, what the series is, okay. Let me discuss it in the next slide. So, this is p into summation of x to the value 1 to infinity q to the power x. So, basically this is the series p, q plus q square plus q plus dash plus this is going up till infinity. So basically by the convergence of this series converges to 1 upon 1 minus q. Actually,
Minus 1.
okay. So actually no, q is less than 1, so it will be 1 minus q only. Okay, wait. So it is actually what it is, p, we will take q as common, so it will be 1 plus q square plus q 1 plus q plus q square plus that. This will be the series. Okay, so we are taking q as common. Now this series 1 plus q square plus this. Now since in the question we are given that q is less than 1, so if q is less than 1, then this series will converge to 1 upon 1 minus q. Now if this, since q is less than 1, now if q was greater than 1, for q greater than 1, then it will converge to q1 upon q minus 1. So this is the condition on Q for which this will series will converge to this. So this will basically converge towards 1 upon 1 minus Q. So now where this sum is going, so probability summation x 1 to infinity q to the power x. So this is going towards pq into 1 upon q minus 1, and sorry, q minus, because q is less than 1, so we'll say 1 minus q, because q is less than 1 in the question. So 1 minus q is nothing but p only. So p will get cancelled. So it is q, which is not equals to 1. So this implies that this is not a PMF. Okay, if there is some doubt, then you may ask. So you are saying that basically this is converging toward 1 upon q minus 1. So when q is greater than 1, then it converges towards this 1 upon q minus 1. But when q is less than 1, then it will converge towards 1 upon 1 minus q only. Okay, is that clear? Okay. Okay, so we will go towards the next function. So what it is? E to the power minus mu to the power x upon x factorial. So okay, B part. So what is probability? X is equals to x is equals to e to the power minus mu to the power x upon x factorial, and mu is greater than 1 and x is varying from 1. Mu is greater than 0 and x is varying from 1 to, am I correct? Mu is greater than 0, x is varying from 1 to 3. Okay. So since we know that since this is exponential part, so exponential will be always be positive because it is in exponent, so it will always be positive. So this first term will be positive. Since mu is greater than 0, so its every power will be always be greater than 0. Since x are 1, 2, 3, so this factorial will always be positive. So no doubt clearly this probability x is equals to x will be positive. So there is nothing to prove for that. Now, what about the summation? So, if we are considering summation over x, probability x is equals to x. So, which is basically summation x varying from 1 to infinity e to the power minus mu to the power x upon x factorial. So, this is basically e to the power minus mu. Summation x is equals to 1 to infinity mu to the power x upon x factorial. Now, what the formula exactly we have, that the series summation x to the x from 0 to infinity mu to the power x upon x factorial. This is basically e to the power minus e to the power mu. So this is e to the power mu. This series is equals to mu to the power e to the power mu. But here we have a one less term. Here the series is the value of x is starting from 1, not from 0. So here we have one less term. So from this series we can calculate that summation for x to the x value 0, it will be mu to the power 0, which is 1 upon 0 factorial. So this is 1 plus summation x 0 to 1 to infinity mu to the power x upon x factorial. This is equals to e to the power mu. So from here we can calculate that summation x to the value 1 to infinity mu to the power x upon x factorial. This is equals to nothing but e to the power mu minus 1. So we'll put it here in this expression. So for that, probability x is equals to x is equals to e to the power mu minus mu actually into what the summation was coming, e to the power mu minus 1. So this was the term, e to the power mu minus 1. We are putting it here, and here this is e to the power minus mu. So here when we multiply it, it is 1 minus e to the power minus mu. So which is again not equals to 1. So this implies it is not a PMF. Okay, so these two functions, these two probability mass functions are not PMF. These two are not PMF. Now we'll consider the other ones also. So we'll consider C part. So what is the C part? Probability x is equals to x is equals to NCX. Uh, 1 upon 4 to the power x, 3 upon 4 to the power n minus x. 1 upon 4 to the power x, 3 upon 4 to the power n minus x, and x is varying from 0 to n, and x is varying from 0, 1, 2 dash. Now since this ncx is nothing but ncx is nothing but a combination term, so it will always be positive. Since this is 1 by 4 constant, positive constant, its powers will be positive always, and 3 by 4 is again a positive constant, so this power will again be positive, so no doubt this function will always be greater than 0. Now what about the summation part? So we'll consider the summation is running from 0 to n actually, where it is going towards n. This is not an infinite series, it is a finite series. Now ncx 1 upon 4 to the power x, 3 upon 4 to the power n minus x, which you can see is basically a binomial expansion. You must be aware of. Okay, let me add a new slide. So this is binomial expansion. The formula for binomial expansion is, so what it is, a plus b to the power n is nothing but summation ncx a to the power x, b to the power n minus x, where x is varying from 0 to n. So this is basically the binomial expansion. So here for our expansion, what it is, this is ncx 1 upon 4 to the power x, 3 upon 4 to the power n minus x. So it is basically equals to probability x is equals to x summation of this over x going from 0 to n. So this is nothing but 1 upon 4 plus 3 upon 4 to the power n, and this is nothing but 1 to the power n, which is equals to 1. So hence it is a PMF. Basically this function is a PMF function. Again for the D part, what it is, probability x is equals to x is 6 upon pi square 1 upon x square. 6 upon pi square into 1 upon x square, where x is varying from 1, 2, 3 and infinitely. So since 6 upon pi square is a positive constant, x is always positive, so the whole term will be greater than 0, so there is no doubt in that. What about the summation? So if I consider the summation from x to the value 1 to infinite, 6 upon pi square can come outside 1 upon x square. So basically this is a series. So this is a very famous series which converges towards pi square by 6. So this series basically converges towards pi squares by 6. So this will be 1. So it is a PMF. So if you guys want that I should consider the proof that this series goes towards pi square by 6, then I will explain it. This is like you can also search it. The proofs are available online also. You can go through that proof and also like find out that how this series is going towards pi square by 6. Or otherwise, if you guys insist, then I can prove this now also if the time permits, because we have done how many questions? We have done 7 questions, and I just want to cover 3 more questions. So if you want that I should like give the proof of this series in the next class, you just remind me to give the proof of this series, the convergence of this series towards pi square by 6, then I will explain that to you. Is that fine, or I should explain it now only? Is that fine?
Yes, ma'am.
Okay. So, okay, I'll move towards the next question. So 3 babies are given a weekly health check at a clinic and then returned randomly to their mothers. So basically, there are 3 babies, B1, B2, and B3. and their corresponding mothers be M1, M2, and M3. Now, what is happening that they are given for the like checkup and they are returned randomly to their mothers. Now, what is the probability that at least one of the baby goes to the right mother? So first of all, we'll consider an event AI that ith baby goes to right mother. Okay, so let us consider the AI to be an event that ith baby goes to right mother. So A1 will be that first baby goes to the right mother. A2 will be that the second baby goes to the right mother, and the third will the A3 will be the event that the third baby goes to the right mother. So what is the probability that at least one of the baby goes to the right mother? So at least one of the baby means they are asking that what is the probability that A1 union A2 union A3, because at least one they are asking. So it can be one, it can be two, it can be three also. So they are asking that what is the probability of A1 union A2 union A3. So by the formula of the probability of the unions, which is we all know that this is probability of A1. This is done in week 1 lecture. Probability of A2 plus probability of A3 minus probability of A1 intersection A2 minus probability of A2 intersection A3. Let me write it here. Minus probability of A1 intersection A3 here plus probability of the intersection of all the three. Now the main thing is how to calculate these probabilities. Now A1 will be the event that the first one goes to the right mother. So if okay, let me explain it in the next slide. So if first one probability of A1 means the first one the this is B1, B2, B3. This is M1, M2, and M3. So if the first one goes to the right mother, okay. So first of all, what is the probability? It's what are the total number of outcomes that first one can go? So it can go to M1, it can go to M2, it can go to S. So total number of possibilities 3. Okay, so what they are asking that what is the probability that the first one goes to the right mother? So what are the total number of possibilities? So okay, wait. So this is another way. So what it is that the first one can go to M1, M2, or M3. So actually, the first one has the B1 has 3 number of possibilities. It can go to M1, it can go to M2, it can go to M3. Again, what about B2? Now let B1 go had gone to any one of the mothers. Now what are the total number of outcomes for B2? B2 has two possibility. It can go to other two. Now B3 has only one possibility. So these are the total number of possibilities. So total number of possibilities are 6. Now what are the probability? What is the probability that what is the favorable outcome that the first one has gone to the right mother? So B1 has already gone to M1. Now how many possibility B2 have? B2 has two possibilities, this one or this one. So B2 has two possibilities. And how many possibilities B3 have? B3 only have one possibility. So this is basically 2 by 6. So this is 1 by 3. So this is the probability of A1, which is equals to probability of A2 by the similar argument, and this is equals to the probability of A3 also. So this is 1 by 3. Now what about the probability? So what about the probability? What the other things are? Probability of A1 intersection A2. So probability of A1 intersection A2 means that the first one, so total outcomes are again 6. Now what is A1 intersection A2 is that first one has gone to the right mother. So for first one there is only one possibility. Second one also get to the right mother. So this is one possibility. And third one also goes to the right, because third one do not have another possibility, because all the previous two mothers are already been they have already got their child. So third one already only has the only one possibility, that is m3, which is 1. So it is 1 by 6, and by similar argument only we can say that this is probability of a2 intersection a3, and this is also probability of a3 intersection a1. Now again, the probability of A1 intersection A2 intersection A3. So which is that the all the three goes to their mothers. So the total is outcome is 6. Then first one goes to one mother, second also goes to one. So the number of favorable outcome will be again 1 into 1 into 1. So this will be 1 by 6. So by putting the formula, so this will be so so again, by putting into the formula, this will be probability of A1 union A2 union A3. So it is 1 by 3 that came out there, plus 1 by 3 plus 1 by 3 minus 1 by 6 minus 1 by 6 minus 1 by 6 plus 1 by 6. So this get cancelled. So this is 3 by 3, that is 1 minus 2 by 6. This is 1 minus 1 by 3, so which is 2 by 3. So this is the probability that at least one of them has gone to the right mother. So the question 8 is already, so we have discussed it. Now question 9. So what this question is saying, that let x be a random variable defined on a probability space, and f is a sigma algebra on omega, p is a probability measure on omega f. Now suppose that f is a CTF. So basically they are saying that suppose f is a CTF, then they are asking that f is always strictly increasing function on R. So what strictly increasing means? Now if strictly increasing, what this means? So there is a difference between increasing and strictly increasing. So it strictly increasing means that if x1 is less than x2, this should imply that fx1 is less than fx2. So here the inequality should be strict. Here this inequality is strict inequality. This function is strictly increasing. However, for increasing function, when a function is increasing, if x1 is less than x2, this implies fx1 is less than equals to fx2. Basically, it also includes the equality. So this is not strict. So this is the definition of increasing, and this is the definition of strictly increasing. So in the question, it is asking that f is always strictly increasing function. No, because in the definition of distribution function, we have studied this property, that the distribution function follows this property, the increasing property. So a distribution function should be increasing by the property as we have already discussed. It may not be strictly increasing. And by the examples which we have already considered, see here we have considered one example. Okay. Here only by example we can give. So this function. So this was a distribution function. This in option B it was given that this is a distribution function. However, the function is not strictly increasing. So there are points x1 here, x2 here, such that fx1 and fx2 are both equal. However, x1 is less than x2, but the fx1 and fx2 are equal. So they are not strictly less than fx2, but they are equal. So here the fx is increasing, not strictly increasing. So this is a distribution function. So for that, we can also give this example that this function is strictly increasing. The function is increasing, and it need not to be a strictly increasing function. So the option A is wrong. Okay. F is always differentiable function on R, so there is no condition on F. However, the condition on F was that it is right continuous. It is not needed to be a continuous function also. So how it can be always differentiable? So this option is also incorrect. f is always right continuous function on R. So this is correct by the fourth property of the distribution function. It should be a right continuous function. Now, what the fourth part is saying, so it is limit x tends to, fourth part, D part, limit x tends to a minus f of x, so f of x. Let me consider this also. So this can be written as limit at h tends to 0 f of a minus h. Basically, this can be written as this. We are just changing the limit. Okay, we are just replacing x by, okay, we can write it like this way only. We are just replacing x by a minus h. So x is a minus h, so we are just saying this to be o. There x tends to a negative here, so this h will tend towards 0. So this is the limit and this is the thing. So now this is nothing but limit h tends to 0, probability x less than is equals to a minus h by the formula of distribution function. This is nothing but this. Now what we are seeing, this h is tending towards 0 and x is less than is equals to a minus h. Now h is tending towards 0 but h is not 0. It is not equals to 0. So this probability is nothing but probability x less than a, which is equals to probability x less than is equals to a plus, sorry, minus, we are just subtracting it, the probability of x is equals to a here, so which is nothing but, so limit x tends to a minus fx, nothing but probability x less than is equals to a minus probability of a, which is nothing but f of a minus probability of x is equals to a, x is equal to a, which is nothing but the fourth option, which is already given in the question. So this is correct. Okay, so this is question number 10. So here we will see that how we can prove a function from omega uh, to r, a random variable. So this is basically function x, which is given as, so first of all the sample space is given to be h till tt ht th. So basically x, what x is? X is basically a function from omega to r. Okay, so how this x is working? So the x of, since omega have h, tt, ht and th. So x is taking h, where x is taking, it is counting number of h's in omega. So it is 2. Okay, and x is taking tt, since there is no h, so it will be 0. X is taking ht to 1, since there is 1 h, and x is taking th again to 1, since there is 1 h. So this is the basically the random, this is basically a function from omega to r. Now we need to prove that whether we need to show that this is a random variable. Now in order to show that it is a random variable, what we need to show, that we need to show that this set omega such that x omega less than is equals to a, this set belongs to the, see omega is a sample space and S is a class of subsets of omega. So we are basically considering here omega comma S to be the measurable space. Or we can say this S to be a sigma algebra. Okay, so this is omega S and S is a sigma algebra. So what we need to see that this set omega such that x omega less than equals to a, which I have already mentioned in the theorem, this belongs to S. We need to only say, and what S is in the question, it is given that S be a class of all subsets of omega. So basically it is nothing but power set of omega. So how S looks like? This is power set of omega, which is nothing but it contains the phi set, it contains the whole set, and it consists of all the subset. Other than these, all the subset it will contain. That is, it will contain head head, tail tail, head tail, tail head, and also the head head, tail head. All the subset it will contain. So let me write it. So what this will be? This will be all subsets of omega. Okay, so we need to see that whether this set belongs to S or not. So A can be what? Let me consider this omega such that x omega less than is equals to A. This is equals to what? Now let us consider this A to be less than 0. So if this A is less than 0 means what we need to find? That we need to find those omegas such that x of omega is less than equal to some quantity which is less than 0. So this set will be phi, because there is no quantity here which is having a number less than 0. So this will be 0, this will be phi, and if this A is greater than equals to 0 and less than 1, so how what we are saying that omega such that x omega is less than is equals to, if A is 0, then this is omega such that x omega is less than is equals to 0. So how many elements are there in the sample space such that x omega is less than equals to 0? So x omega is equals to 0 for tail tail. So this will be the tail tail only, because if I consider up till 1 the quantity which is less than 1, so there is no quantity which is attaining a number between 0 and 1. So there is again the next number is 1 only, before that there is nothing. So we'll consider that. Now apart from this, if I consider A to be greater than equals to 1 and less than 2, so we are considering the number which is less than 2. So how many events are there which is having a value less than 2? So which is tail tail, head tail, and tail head. So it will be tail tail, head tail, and tail head. Now if I consider A to be greater than equal to 2, so for A equal to 2, so I'm considering what are the omega such that x omega is less than equal to 2. So all the elements will come, because for all the elements the x omega is less than or equal to 2. So there will be the whole sample space, and we see that this phi is also a subset of also an element of S. This belongs to S, this belongs to S, this belongs to S, this also belongs to S. Hence this whole set belong to S for all A. This implies that X is a random variable. So this was basically how we can check that whether a function which is defined from omega to R, whether it is a random variable or not. So it can be checked using this kind of method. Okay, so I will be stopping it here by doing these 10 questions. I hope you understand the things. And if there are some doubts, then you may ask.
Ma'am, can you explain the last option for the previous question, ma'am? D option.
Okay, last option for the previous this one.
Yes, ma'am.
Okay. So what it is saying, that limit x tends to a minus fx, what it will be. So basically what it is saying, like if I consider this function fx, now any function it can be any function, I'm just considering it. Now what is happening with the domain? Now let us take a to be here. Now how can we visualize this? X tends to a negative. What does it mean? It means that the value, the x is approaching from the negative side of a. That is, x is approaching from here. Now when x is approaching from here, where the fx is going, we need to check that where the fx is going. So this basically means this is basically the meaning of this limit. So now if I replace x by a minus h, then it can be also, this limit, same limit can also be written as limit h tends to 0 f of a minus h. Okay, this also means that we are finding out the value of the function where the values of this is approaching from the left side of the a. Since here the h is going towards 0, means when h is going towards 0, where the a minus h, where it is going to, this is again going towards a, but from where it is going towards a, from the left side, because what we are doing, we are saying a minus 0.5, we are saying, we are considering a minus like 0.2, and this quantity we are which we are subtracting, this quantity we are tending this quantity towards 0. So this a minus h is going towards a, but from the left side. So just consider that this is a here. Now if I want to go towards a from the left, then I will say that a minus h and limit h tends towards 0. Okay, then I'm approaching towards a from the left side. Now, if I want to approach from right side, then I will say that limit h tend towards 0, a plus h. This means I am approaching a to from the right side. Okay, so basically this limit, what limit x tends to a minus means that x is approaching, oh, sorry, that this x is this x is approaching a from the left hand side. Now same argument can be, now we can replace that same argument by this limit, that limit h tends to 0 f of a minus h. That means that this is the function in the this argument, this is approaching towards a from the left hand side, and here we are taking the h tends to 0 because this is more convenient limit to handle with as compared to this limit. Now this, if you understand this concept, then what it is, this is limit h tends towards 0, and this is f of a minus h, means probability that x is less than is equals to a minus h. Okay, now this h is going towards 0, but this h is going towards 0, but h is never 0. H is never equal to 0. It is just going towards 0. So what it is saying, that x is less than is equals to a minus h, means yeah, this quantity limit, since h is going towards 0, so x is less than is equals to a minus h. This quantity is always less than 1. So here we are considering the probability that x is strictly less than a. It can never be equal to a, because it will be equal to a when h is 0. When h is approaching towards 0, then it is never going to be equal to 0. So it is always this quantity, which is, this will always be less than a. So which is nothing but probability x less than is equals to a minus probability of x is equals to a. So that's why basically it is the way to write that this is open at a, that we are not considering this point a here, we are just considering the points which are less than, strictly less than a. So basically what we are doing, we are just removing the point a from the value which the value of x is taking. We just remove the point a from this probability x less than equals to a, then it will be the same thing. So I think this, you understand this. This is a just way of
Yes, ma'am.
visualizing that. This is how you visualize the things, and this is a way of writing it formally in a mathematical way.
Yes, ma'am. Thank you, ma'am.
Okay. Any other doubt you have? Any other person? Any doubt? Okay, so I hope the things are clear to you. If there are some doubts, then you may ask it, and I will be happy to like answer those questions. And I hope that next classes you will be like attending the lecture, and you will be coming back by already seeing the questions which are already there in the assignment. And if there are some doubts today also, then you may ask it, or you may discuss it at the next class, which will be happening next Tuesday. So, okay, then if there are no doubts, I will be ending this meeting. Okay. Thank you, all of you, for attending
Thank
the
you,
lecture.
ma'am.
Okay.
Thank you, ma'am.
Okay, thank you.